Okay, this is our example for section 7.3 out of the NICE textbook. This problem states that we have a unity feedback system. Here is our open loop transfer function g of s. It's given as k times s squared plus 3s plus 30 over s to the nth times s plus 5. And this system is to have 1/6000th error between the input of 10 times t times u of t and the output in the steady state. And it asks for a few things. Part A, it says to find k and n to meet that specification. So k is right here, and then n is this exponent on s. So basically they're wanting us to find the system type. Remember, the system type is determined by this value of n. And then they also want us to find k sub p, k sub v, and k sub a. So those are just the steady state error constants. Okay, so that's what we're going to find. So let's start with part A first. Alright, so when it tells us that it wants the system to have 1/6000 error between the input of 10t u of t and the output in the steady state, basically it's saying that it wants the steady state error, which is e sub ss, or e with t equal infinity. It wants that to equal 1/6000. Okay, so we know that. And then we're given this input. So we have 10 times t times u of t. Since we have this t right here, that means we've got a ramp input. Okay. Now, if you remember back from the lecture for 7.3, using the error constants that we talked about, if we have a ramp input, our steady state error can be rewritten as 10, since we have this 10 here, over kV. Okay. So now if you notice, we have an equation for steady state error here, and then we have another one here. So we're going to set those two equal to each other. So we're going to have 10 over kV equal 1/6000. And with that, you can solve for kV. So kV is going to be 60,000. Alright, so now we've got that. Now what are we going to do with that? Well, let's see what kV is equal to. So if you remember, kV is equal to the limit, as s goes to 0, s times g of s. Now we have the equation for g of s that was given. So let's go ahead and multiply that by s. So we're going to have s times k times s squared plus 3s plus 30 over s to the n times s plus 5. Okay? So now we've got that. Now the only way that we can make this kV be this finite number here, this 60,000, is to have n be equal to 1. Okay? Because if n was equal to 0, then this numerator would go to 0 because this s would not be canceled out. Okay? So we don't want that. That wouldn't make any sense. And then if n were equal to 2, we would end up with this s in the denominator. Right? This one would cancel, but this one would still be here. We'd still have 1 here. So then we'd have 0 in the denominator, which would lead kV to be infinite. Okay? So neither of those options are good choices. So n equal 1 is our only choice. Okay? So with that, we're going to say n is equal to 1. Okay? And if n is equal to 1, let's rewrite this out. Then we can get rid of this and this. Okay? So now we've got that and that. So now if we do our limit and have s go to 0, basically we can say that the 60,000, since that's what kV equals, remember this is kV essentially, that's going to equal k times 30 over 5. And we get that because we're setting s equal to 0 when we do our limit. Okay. So now we have the simple equation. We have one unknown, which is k, so you can easily solve for k. And we get that k is equal to 10,000. Okay. So that's how we do part A. So we've got a type 1 system, and then k is going to be 10,000. Okay. So in part B, we want to know what kp, kv, and ka are. Let's do that. So kp, if you remember, if we go back to this table that we had, if I can switch back to it. Yeah, I can't switch back to it. But kp, if you remember, is going to equal the limit, as s goes to 0, of g of s. Okay? So we know what g of s is. We have k, we have n now, so we can plug those in. So we're going to have 10,000 times s squared plus 3s plus 30. We're going to put that over s times s plus 5. And then if we do this limit, let s go to 0, this goes to 0, this goes to 0, this here also goes to 0. So with this one, we're making the denominator go to 0. So anything divided by 0 is going to go to infinity. So kp is going to be equal to infinity for this system. Okay. And k sub v, the equation for that, if you look back in that table that we did during the lecture, we've got the limit as s goes to 0 of s times g of s. Right, so let's multiply g of s times s. So here's the s, and then we've got the 10,000 times s squared plus 3s plus 30 over s times s plus 5. Okay. Now in this case, if you look, this s will cancel with this one. Okay. And these other s's will go to 0. So what we're left with then, once you do the math, is going to be 60,000. Okay. And that makes sense because if you notice, we scroll back up here, we had already found that right there. Okay. And then finally, k sub a. Equation for that is going to be the limit as s goes to 0 of s squared times g of s. So now we just need to multiply g of s times s squared. So we're going to have s squared times 10,000 times s squared plus 3s plus 30. Put that over s, oops, times s plus 5. Okay, and we're going to do the limit of this. Theoretically, I should be writing limit here, but I'll be. Y'all know I'm not good at doing that stuff. Okay, so we're taking the limit of this. So now let's see what all cancels. One of these s's will cancel with this one. Okay. So now if we look, since this s is left in the numerator, when we're making s go to 0, that means this whole numerator is going to go to 0. So k sub a then will be equal to 0. So this is just an example of how you can use these error constants to find different parameters. And then using these error constants, you could figure out what your steady state error would be, all different sorts of things. Okay? All right. So that is the end of Chapter 7 material. Okay? See y'all in class.